Lambert's law is associated with the intensity of incident light on the absorbing solution and that of intensity of transmitted light. That means if we take an absorbing solution, if suppose this is the beaker and if we take the absorbing solution in this beaker, let I0 be the intensity of incident light and I be the intensity of transmitted light. Definitely this I is less than I0 because some of the radiation get absorbed by this absorbing solution. Now how this absorbing solution is prepared? The absorbing solution is prepared by dissolving the solute. Usually this solute is colored because we are going to incident light that is the electromagnetic radiation from 400 to 800 nanometer radiation. The colored substance, they absorb the radiation in this visible spectrum, and here we have to prepare that solution in non-absorbing medium, that is solvent. Our solute which is having color and the solvent which is non-absorbing, and hence in the when the solution is prepared, only the solute particles which are present in that solution, they absorb the radiation. Now in this case, when I0, the incident radiation is passed through this absorbing medium, then some of the radiation get absorbed and some get transmitted, and this intensity of transmitted light I is always less than I0 because some of the radiation get absorbed. Let L be the path length of this solution. L be the path length of this solution. Then according to Lambert's law, when monochromatic radiation passes through absorbing solution, the intensity decreases exponentially with thickness of the absorbing medium. When monochromatic radiation passes through absorbing solution, the intensity decreases exponentially with thickness of this medium. Or mathematically we can say the decrease in intensity, we can show intensity decreases di with thickness dl is proportional to intensity of incident radiation. Intensity of incident radiation. Or we can replace this proportionality sign by di upon dl is equal to, let K1 be the constant I. You know this, here we have to show the negative sign. There is decrease in intensity and hence we have to show the negative sign, and hence we can write di upon I is equal to K1 dl. We can integrate this solution. Integrating we obtain integral minus integral di upon I is equal to K1 integral dl. K1 being constant we can take out, and this we know very well know the integration of di by I, it is ln I raised to the Neperian logarithm to the ln I is equal to K1L plus C, where C is the constant of integration, and we can find out this constant of integration by initial conditions. Initially when the thickness is 0, I0 तिथं काहीच absorption होणार नाही आहे, म्हणजे I0 will remain as I0, and because of that here again negative sign is there. Negative sign, only integration of di by I is equal to ln L, and hence we get by using the initial conditions KL minus by taking the initial conditions into account, that is that when L is equal to 0, that means no absorbing medium is there and intensity of transmitted light is same as that of intensity intensity of incident light. And hence, by using these, we can find out the value of constant of integration ln I0. Taking this to the left hand side, this becomes ln I0 minus ln I is equal to KL. Now the subtraction of logs is equal to the ln I0 upon I is equal to KL. But since we are interested in the transmitted light, we will take the again its reciprocal, that is ln I upon I0 is equal to minus KL, or as stated by Lambert's law, the intensity, or when a monochromatic radiation passes through the absorbing solution, there is decrease in the intensity of transmitted light exponentially. Here the ln, that is logarithm to the natural base or Napoleon logarithm, this becomes I upon I0 is equal to e raised to minus KL, or I is equal to I0 e raised to minus KL. Now this is the relationship of the transmitted light with incident light with thickness of absorbing medium. Very similar to this, another law which is given by Beer's law. That law is called as Beer's law. We will discuss this Beer's law. Beer's law. Now, in case of Beer's law, here there is a decrease in intensity of radiation with increase in path length. And here this Beer's law is related with concentration of the absorbing solution. Now again we have to prepare the absorbing solution by dissolving the absorbing solute in non-absorbing solvent. That means the solution is absorbing solution, but the solvent is transparent or non-absorbing. The same solution is there. Let C be the concentration of this solution. C is the concentration of this solution. I will take, to avoid the confusion of constant integration, this C is the concentration of the solution. Now as the concentration increases, definitely number of absorbing molecule also increases, and definitely the intensity of transmitted light goes on decreasing with increasing concentration. The same is stated by Beer. According to Beer's law, when a monochromatic radiation passes through absorbing solution, the intensity decreases exponentially as the concentration of the solution increases. Here Lambert has stated this the same, that is the decrease in intensity of the transmitted radiation with path length of this absorbing solution. But in case of Beer's law, he also proposed that there is decrease in intensity of this incident radiation with increase in concentration of the solution, and hence the same type of equation is there. That is, here we have mentioned along with path length, here we have to mention the decrease in intensity along with concentration, and same type of equation is obtained, that is I is equal to I0 e raised to minus K2C, where C is the concentration of the solution. Same type of equation is there. And Beer, Lambert, both these laws are very important in case of absorbing solution, and the combined law is called as Beer-Lambert's law. Beer-Lambert's law, which takes into account the path length of the solution as well as the concentration of the absorbing solution. And according to Beer-Lambert's law, we obtain this equation I is equal to I0 e raised to minus KCL C is the concentration of this absorbing solution. L is the path length of this absorbing solution. When a monochromatic radiation passes through the absorbing solution, the intensity of transmitted light goes on decreasing exponentially with also the product of concentration and path length of the solution. Both factors are important for absorbing solution. One is the path length. The law is separately given by Lambert. The another term is concentration. With increasing concentration, number of absorbing molecules also increases. Definitely there is decrease in transmitted light. As path length increases, number of absorbing molecules again increases, and definitely there is decrease in the intensity of transmitted light. This law is very important in case of calorimetry and spectrophotometry, and mainly this law is applicable for dilute solutions. The concentration of the solution should be near about 0.01 molar or less than that. Then this Beer-Lambert's law is applicable to these absorbing solutions. Now further, there should not be association of the solid particles or dissociation of solid particles. All these limitations are there, but this law is applicable very nicely for dilute solutions. Now this R is equal to I0 e raised to minus KCl, Beer-Lambert's law. Now we can write the same as I upon I0 is equal to e raised to minus KCl. Or now to convert this into the logarithm again, here e is there, taking e as base. You might knowing the logarithmic rules. This we can write as ln, that is log to the base e, natural logarithm or Neperian logarithm I upon I0 is equal to minus KCl, To convert this log to the natural base to base 10, we have to multiply by 2.303. We can write as 2.303 log of I upon I0. Now the base is 10. It is applicable that we are not able here to write the base 10. 2.303 log to the base 10 I upon I0 is equal to minus KCl, or same we can write as log of I upon I0 is equal to minus K upon 2.303 Cl. This term K upon 2.303, this is constant, K upon 2.303. Or same we can write, suppose instead of this negative sign, if we take this negative sign to this side, what will happen? This will be log I upon I0 is equal to K upon 2.303, which is one more constant, C that is concentration, L is path length. This term log of minus log of I upon I0 minus 1, which is the multiple we can take as exponent of I upon I0, and the same we can write as log of I0 upon I is equal to this K upon 2.303. This term is another constant this constant is known as epsilon. Epsilon, that is, and this term log of I0 upon I is called as absorbance. A is equal to epsilon Cl. This is very important equation in case of calorimetry. A is absorbance. What is absorbance? Absorbance, it is either log of I0 upon I or minus log of I upon I0. Both these terms are equal. This term and this term. Absorbance. Absorbance is equal to epsilon. This epsilon is a constant called as extinction extinction coefficient. Extinction coefficient, and C is the concentration, L is the path length. Now, how we are going to define this extinction coefficient, this absorbance, when concentration is 1 mole per liter, 1 mole per liter, and L is 1 centimeter. That means both are unity. This A is equal to epsilon. This molar extinction coefficient, this term is now called as molar extinction coefficient, since we are taking this concentration as 1 mole per liter. This molar extinction coefficient is nothing but absorbance when the concentration of the solution is 1 mole per liter and the path length of the solution is 1 centimeter. Path length, that means in that case we use the cuvettes. Cuvette, that means the absorbing solution taken in the cuvettes. These cuvettes, these are the containers of glass or pots. In case of calorimetry we can use glass. In case of UV spectroscopy we have to take the quartz cuvettes having the path length of, this path length in that case is 1 centimeter. This molar extinction coefficient is the absorbance of the solution when the concentration of the solution is 1 mole per liter and path length is 1 centimeter. These are some basic terms usually used in the calorimetry. And this epsilon, when measured at highest or maximal absorbing wavelength, then it is called as epsilon max. Epsilon max, and this is the characteristic of that particular solution.